Hello everyone, welcome to this video. My name is Emerson Ahrari, I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate the seasonal shift in the temperature data using harmonic modeling. First of all, you must select your region of interest. No matter where is your region of interest, this tutorial can be used for all around the world. For example, I'm selecting Iran, my own country, through the drawing tools available here. Just draw your region of interest. It is better to select a bigger area because we are going to use some coarse spatial resolution data. So go to search places and dataset and search for Aero 5 data. As you know, the Aero 5 is one of the assimilated remote sensing data available in the Google Earth Engine platform, combines stationary data and satellite and models together and provided noise-free data without cloud impact for long time series analysis. So as you can see, the Aero 5 data for land for non-water area is available with monthly, hourly, and daily version. So I prefer to use the monthly data because it is actually better for the long time series analysis. Import it into the code as a new image collection. If you want to have focus on the study area, let's get started with center.object based on geometry. The geometry refers to the drawing area we made through the geometry or drawing tools available here. Whenever you run a code, map.centerObject allows you to focus on the study area. So there it is. And make a new variable as temperature equals to assign the image collection to the temperature. If you go to the data properties, you can get a lot of information about dataset availability, dataset ID, and dataset descriptions. If you go to the band, you can see the spatial resolution is around 11,000 meters or 11 kilometers, and the target band for us is temperature in 2 meters, that is air temperature. There are two bands. If you're supposed to work with skin temperature or LSD, you can choose this. Otherwise, temperature 2 meters regarded as the air temperature in this study. I'm gonna assess a seasonal shift in the temperature data. Close it and then select the target band using .select function. So the target band is temperature 2 meters and then set a period of time for the harmonic analysis. If you back to the data properties, here you can see that this dataset is available 9050 by now. But here I'm gonna do a 40 years time series analysis from 1980 to 2021, for example. From 1980 to 2021. Almost 40 years considered for this study. If you want to see how many temperature data is available for this period of time, that size allows us to see the number of images. We have 492 images available for this period of time with monthly temporal frequency. And also, if you want to see or get a print or preview from each data, a list of data, here you can print the first 20 images. First 20 images using that limit. Limit 20 only prints 20, the first 20 images available on Aero 5 image collection. Here, as you can see, for all datasets, we have one image. It is temperature at 2 meters. Now we want to calculate the seasonal shift, but before that, we must calculate some temporal parameters such as, for example, the date of each image, the fraction date of each image, the phase of each image, and sine and cosine variables that explaining the seasonal variations in the temperature data. So make a new variable, for example, parameters equals to, first we must make a list of independent and dependent variables. And here the dependent variable is temperature and independent variable belongs to different criteria related to the time. So get the temperature data, all 400 temperature data brings here, and then we make a loop through the function to calculate independent and dependent variables. So each input image from temperature data named as an IMG into the loop structure. So now from each image we want to extract its date. As you can see in the properties, the acquisition date or the date of each image already stored in the system time start property. Now if you want to get date of each image, you must actually from each input image use the get to get a new property that is system time start. System time start. And if you want to have it as a date format with a date format, Earth engine.date used, just like that. So now we have the date of each image, and in the next step we must calculate the date fraction or phase, a new parameter. This is the phase. Phase calculates the date position in a year. For example, here bring the date and calculate its position in a year using that get fraction. The unit is based on a year, and get rid of the time zone. And after the phase calculated, you must convert it to the radian format using dot multiply using this equation. Dot multiply to multiply math pi. There it is. So once the phase calculated, now we must get the sine and cosine value for each phase. So here the sine equals to get the phase and calculate the sine, and cosine get the phase again, this time go for cosine, just like this. The sine and cosine actually expressing the temporal variations of temperature, not in this step, but in the next step that we want to get regression between these independent and temperature. The sine and cosine allows us to explain or actually discuss about the seasonal variation in the temperature data. That's why these two parameters are very, very important in our analysis. So, and another one is, for example, the time equals to the time explaining the differences between each date and also an origin date. For example, could be any year. So here, for example, the date that difference calculate. We want to actually get the differences between each date with the origin date. For example, here could be 1970. For example, here Earth engine date calculate difference with the origin. For example, here could be 1970, and the difference should be calculated based on the number of the years. So there it is. The time, sine, cosine, and phase, these are all available. Now I'm gonna have a list of independent variables in a list in an image stack format. That's why Earth engine.image.cat should be used. Inside a stack layer, I will have an image for sine, an image for cosine, for time, and finally a constant value. So these are independents we're supposed to use in a regression equation. And finally, the function returns all independents with the dependent variable that is the temperature here, with the properties of input images, specifically system time start and system time end. System time start and system time end, just like that. So these parameters, now for each date, we have a list of independent and dependent variable. So now we must calculate the regression relationship between independents and dependents. So here, make a model equals to get parameters that is available for 40 years and then import it into the model using reducer dot linear regression. So in the linear regression, we need two values. The first, number of x. The x here shows or means the number of independents, that is 4 already mentioned. And number of y refers to the number of dependents, that is 1, that should be temperature. 1 refers to the temperature, and first 4 back to independent time-related variables. So the time parameters and temperature imported into the linear regression to explain the seasonal shift in the temperature data. So get the print from model to see if there is any problem or not. Hopefully the calculation is done without any syntax error. We have a coefficient with the array structure because it has 2 dimensions. So we need actually extract the coefficients belongs to each independent parameter, specifically sine and cosine. So make a new layer as, for example, coefficients equals to, from input model, select the coefficients first, and then as it has an array structure, array project help us to select the first dimension, and dot array flatten allows to make an image stack from the coefficients. So the coefficients, the first belongs to sine image, the next cosine image, and the third is the slope of changes over the last 40 years, and the final one is the offset. There it is. And now to do the visualization, map.add layer could be useful. From coefficients, I'm gonna select from just coefficient first, clip it based on the geometry or region of interest. Leave the visualization parameters empty for now, and the layer name is coefficients, and use the false at the end to avoid automatic visualization. Save the code, but remember to use the double for the independent, because the independent layer stack including various values that are not very close or match or consistent to each other. That's why we must use the double for independent to avoid any further problems for the next steps. Remember to save the code and run it again. When you are doing harmonic modeling, it is very important to have a right interpretation for the output. Technically, there is not a big problem in calculations, and as you saw that, just some simple temporal parameters calculated here. So, but here we have a problem, image.select the coefficients. Yeah, something missed here. Try to run a code again. This time we have no problem. open the layer setting, and as you can see, all 4 coefficients available. For example, first I'm gonna show the slope of temperature changes, or how much temperature changes over the last 40 years here. So then increase the contrast using 90% of values. As you can see here, the values ranges based on 90% of values. Actually, the minimum and maximum showed here. Click on apply and check it on to see the temperature variation over the time. So here we have a grayscale image that bright areas shows higher, actually bigger changes, and some actually darker area shows in a way, for example, smaller changes. For example, in the northwest of Iran and west of Iran, we have a bigger change in terms of temperature variations rather than or compared to the east and center part of the country. So as you can see, the slope is a useful thing to interpret the amount of changes occurred in the temperature. If you go to my YouTube channel, you will find a lot of information about the time series analysis and temporal changes that helps you to do monitoring process using simpler method and regression technique. But in this tutorial, the seasonal shifts that could be explained by sine and cosine coefficient is more important. But before go through the seasonal shift, you can see here the darker region and brighter region. For example, when I select one of the bright region or one of the bright pixels, here in the inspector, if you switch already, you can see the corresponding value for the sine, cosine, and also the slope. The positive slope, meaning that the temperature has an increasing trend in this pixel over the last 40 years. But if the slope is negative, the negative slope means temperature has a decreasing trend over the last years. But here, as you can see, in the most of the regions, temperature had an increasing trend in different areas. Bigger increase, as you can see, or higher increase, brighter, and lower or a smaller increase, actually with a darker pixel already showed here. This is what you must know about the slope. But the next is about the seasonal variations. The phase information, the temperature phase information already saved into sine and cosine coefficients that could be very, very useful to interpret seasonal changes in the temperature data. The main difference between this tutorial and the previous tutorial on my YouTube channel is about related to the seasonal change detection or seasonal shift analysis that never produced before on my channel, and here you can get enough information. So here I will have a sine image. I'm gonna increase the contrast first and then click on apply. And here, as you can see, the sine image ranges from minus to positive or negative to positive values. When the sine is positive, meaning that the temperature peaks shifts to the shifts earlier, for example, from spring to mid of the summer. But when the sine value is negative, meaning that the temperature peak shifts to a bit later in the year. For example, the second half of summer or the early fall. That's why how we can express it or interpret it. But the important thing is that you must consider the sine and cosine together. As I mentioned earlier, negative value shows shift toward a little late, toward the end of summer or early fall, and also the positive value shows a shift to the earlier in a year, for example, early summer or late of spring. So now switch to inspector again and select a pixel from the sign image. Hopefully in the inspector you will be able to see the phase information, sine and cosine I mean. So as you can see, there is a big difference between sine and cosine. That meaning that we have a very big variations from one season to another season about the temperature data, meaning that we have a high fluctuations in terms of temperature from one season to another season. And also when the cosine and sine, both of them are negative, it significantly express that the temperature peaks shifting toward the end, toward a bit later, toward to end of summer, toward to early fall. And also this is showing a shifting in a temperature peak from the summer to a bit later. That's why maybe it's related to the climate change or something else. But just here I'm trying to give you some insight about phase interpretation that should be very, very important things in the time series analysis, because we must know how much seasonal behavior in the temperature, precipitation, and snow cover changing during the time. So there it is. Or another pixel here. So this is a good example. In this pixel, one of the phase information is positive and another one is negative. As I mentioned, the positive value shows that the temperature peaks shifting toward the earlier, but the negative shows shifting toward a bit later during the year. So, but as we have a more actually a bigger value in the cosine image, and also as you can see -12, meaning that it is more significant than the sine value. And according to the cosine, we can say that the -12 shows this pixel temperature actually shifting, or a peak temperature shifting toward a bit later in a year, to the second half of the summer or early fall, because its value is stronger compared to what we have in the sine value. So there it is, and also at the same time you can see the variations in the slope that shows the long-term trend, a linear trend that is positive and shows the temperature in this pixel is increasing. So now that was about the interpretation or seasonal behavior analysis using sine and cosine pixels. In the next step, I'm gonna show you how to get export from these coefficients using export.image.toDrive. Couple of arguments should we have here. The first one is the image including the coefficients. That a coefficient is already an image stack, and just you must clip it based on the region of interest, that is geometry here. And the next one is description. The description is again the name of the output. Here could be anything. For example, I named it as Harmonic, and the scale for the output should be 11,000 meter, because the spatial resolution is 11 kilometer. And the next parameter is about the region of interest, that should be equals to the geometry CRS coordinate system EPSG 4326. This is a coordinate system code that you must use for WGS 84, that is same for all around the world. And the next parameter is the folder you want to save your output in. For example, I make a folder as a test, and I want to save the output there. So once the export.image to drive gets ready, click on save and click on run to get the output in the task. Switch to the task, click on run and again on run and wait to see the result. Once the result saved in the Google Drive, the tab's color turned to the blue, and then you can go there and pick up your data and open it up in all the softwares, all the geospatial softwares that you are working with, no matter it is NV, ArcGIS, or QGIS. As long as you are working with the geospatial softwares, you can easily open a GeoTIFF file there. This GeoTIFF layer, including a couple of bands or 4 bands, sine, cosine, slope, and offset, that I already explained how it works and how you can interpret their results. I hope you like this tutorial and thank you for your attention.